Hello, I am Dr. Zenya Worth, and in this video, I will be discussing matrix operations. We will be discussing matrix addition and subtraction, matrix multiplication, transposing a matrix, and finding the determinant of a matrix. Let's start with matrix addition and subtraction. You can only add or subtract matrices if their dimensions are the same. Remember that you dimension a matrix by writing out its rows and columns. A matrix with 3 rows and 2 columns would have the notation 3 times 2. To add or subtract matrices, add or subtract the corresponding elements. In a 3 by 3 matrix, the element in position 1, 1, first row, first column, would add to an element in the second 3 by 2 matrix in the same position 1, 1. The same thing happens for elements 1, 2, 2, 1, 3, 1, and 3, 2. Let's do an example by adding and subtracting 2 3 by 2 matrices. Let's add first. So we have 2 matrices with the same dimensions, 3 by 2. In the first position, we have a 2 and we have a 1. So we end up doing 2 plus 1. 2 plus 1 gives me 3. Let's say row 1, column 2, we have a 5 in our first matrix and a 2 in our second matrix. So that would be 5 plus 2 is equal to 7. And you do this for every element in matrix 1, added or subtracted to every element in matrix 2. The same rules apply for subtraction. In this case, we have 2 in our first position in matrix 1 and 1 in our second position in matrix 2, in our first position in matrix 2. So that would be 2 minus 1, which would be 1. This also works for negative numbers. It is perfectly okay to end up in the negatives. If we have a 3 in this position in matrix 1 and a 9 in the same position in matrix 2, well, since I'm subtracting 3 minus 9 in this case, I end up with negative 6. And that is absolutely okay. Again, you do the same corresponding subtraction for every element to achieve your final matrix. It should have the same dimensions as your initial matrices. To multiply matrices by a scalar now, as we move on to matrix multiplication, you need to multiply every number in the matrix by that value. So it's pretty friendly. If I want to multiply this entire matrix by 2, I multiply every element in that matrix by 2. 2 by 2, 3 times 2, 4 times 2, 9 times 2. Everything becomes double because I'm multiplying everything by 2. So my new matrix should be double my original matrix. However, to multiply matrices together, it gets a little more complicated. First, there's a very specific rule to follow. The number of columns in the first matrix must equal the number of rows in the second matrix. Given a matrix that has m rows and n columns, and another matrix that has O rows and P columns, the n value in matrix 1 must equal the O value or the number of rows in matrix 2. And then the resulting matrix would have dimensions m times p. Let's look at another set of examples. These 2 matrices from the beginning, they actually don't multiply because we have a 3 by 3 matrix trying to be multiplied by a 3 by 2. Since this position 2 is not equal to 3 in this case, we have a 2 for the number of columns in matrix 1 and a 3 for the number of rows in matrix 2. Since those 2 values are not equal, these cannot be multiplied. If we look at another example, in this case, we have a 3 by 2 matrix here and a 2 by 3 matrix here, 2 rows and 3 columns. Since this number 2 in matrix 1 is equal to the number of rows in matrix 2, the number of columns in matrix 1 is equal to the number of rows in matrix 2. Since those numbers are the same, then you can multiply those matrices together, and your resulting matrix is going to be a 3 by 3 matrix. How do we multiply matrices? We perform the dot product of the rows and columns. Step 1, for position 1, 1 of our new matrix, do the dot product of the first row of matrix 1 with the first column of matrix 2. For position 1, 2 of our new matrix, do the dot product of the first row with the second column. You see how this number changes? It is now the second column. But since we're still in the first row, this 1 is going to stay the same. That is the pattern for doing matrix multiplication. You repeat all these dot products until you've done a dot product for every row of matrix 1 and every column of matrix 2. And if you need a reminder, the dot product is the sum of corresponding values that have been multiplied together. Let's do an example. It's easier to visualize. So let's multiply these two matrices that we talked about earlier. Let's do step 1. I want to find the value in position 1, 1 of my new matrix. So that means I need to multiply the first row of matrix 1 by the first column of matrix 2. In this case, I'm doing the dot product of 2 and 5 by 3 and 4. That would be 2 times 3 plus 5 times 4. 2 and 3 are multiplied, 5 and 4 are multiplied, which is 6 plus 20, which is 26, which means that our new matrix for position 1, 1 has a value of 26. Let's do this again. In this case, I'm going to multiply the first row of matrix 1 by the second column of matrix 2. So I'm looking for a final value in the position first row, second column of my new matrix. So my first row dot product of the second column is 2, 5, dot product 6, 9, which is 2 times 6 plus 9 times 5, which is 12 plus 45 is 57. And that goes in position 1, 2 for my new matrix. Let's do one of the values on the second row so we can continue to develop the pattern. The dot product of matrix row 2, which is 3, 6, by column matrix 2, column 1, which is 3, 4, is going to give me the position or the value for position 2, 1 in my new matrix. 2, 1. Row 2, column times column 1. So the dot product of row 2, 3, 6, column 1, 3, 4, is 3 times 3 plus 6 times 4, which is 9 plus 24 equals 33. You can also do that for 12. So now I'm very slowly but surely filling in all my matrix. And I repeat these steps until my matrix is totally finished. And I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 new values. To transpose a matrix, luckily this is pretty fast. You interchange the rows and columns. The notation for a transpose of a matrix is a superscript T or an apostrophe. If this matrix is named A, the transpose would be A superscript T or A apostrophe. To transpose a matrix, you make the rows into columns. So the rows of matrix A are 2 and 5, 3 and 6, and 4 and 9. And I simply move those around until I make those into my columns of my new matrix. So the transpose of this is my first column in this matrix is 2, 5. My second column is 3, 6. And my third column is 4, 9. The determinant of a matrix is based on the multiplication of the numbers in the diagonals of the matrix. This can be very useful for doing things like finding eigenvalues when you take differential equations. In order to take a determinant, the matrix must be square. And the notation for this is either 2 vertical lines, or sometimes you see the DET of parentheses, the name of the matrix. For a 2 by 2 matrix, the determinant is quick to calculate. The determinant of this 2 by 2 matrix governed by A, B, C, and D is A times D minus B times C. You multiply the numbers in the diagonals. You start from top left to bottom right, and then top right to bottom left, and you subtract them. A times D minus B times C. For a 3 by 3 matrix, the process becomes more complicated because you have to take the determinant of 3 2 by 2 matrices within this original structure. For a given 3 by 3 matrix, the determinant is this large expression. Let's try to look more closely at this to determine the pattern. The pattern here is eliminating certain aspects of this matrix and taking the determinant of 3 2 by 2 matrices. So you need to find the 2 by 2 matrix that is not part of the row or column of your initial position. So in this case, we're going to start with position 1, 1, which has a value of A. What I do to help me take the determinant is I actually just draw a line through the row and the column that includes my position 1, 1. So if my position 1, 1 is A, I draw a line through that row 1, and I draw a line through that column 1. Now I'm left with 4 values that make a little 2 by 2 matrix. And I take the determinant of this 2 by 2 matrix and I multiply it by the number in position 1, 1, and that is going to be my first determinant. So in this case, it is A times the determinant of E, I, F, H, my little 2 by 2 matrix, E times I minus F times H, times that whole expression times A is the determinant of my first 2 by 2 matrix. I'm going to leave that alone for now. And I'm going to do it again. So now let's move on to the second position in our first row, which is B. It is position 1, 2. I'm going to do the same thing where I'm going to draw a line through the column and the row that includes B. Once I do that, I only have 4 values left in my matrix that don't have a line through them, D, G, F, I. So I'm going to develop a 2 by 2 matrix with those values and take the determinant of that. So I have D times I minus F times G times by B, and that is the second position of my determinant. I'll do this one more time. I'm still in the first row. I'm always going to stay in the first row. But now I'm in the third column. And that third column has a value of C. I'm going to draw a line through the first row because it includes C. I'm going to draw a line through the third column because it includes C. And I'm going to be left with my 4 remaining terms in the matrix, D, E, G, and H. Take the determinant of D, H, or D, E, G, H, E times H minus E times G, and I multiply it by the position, the initial position that I started with. So remember, you do always need to multiply it by wherever your reference position is. So I do that, and I find the third term of my determinant. I sum all of those determinants together, and I end up with my full expression. However, please remember that there is an additional rule here. For the second term, you actually subtract it. So you have your first term, it's positive, you subtract your second full term, and then you add the last term. So it's a sum, but it's also a difference. So please make sure to remember to always subtract the second term. And this pattern will repeat if you have a larger matrix, plus, minus, plus, minus, plus. So if I do that, then you can find the determinant of the 3 by 3 matrix. I highly recommend for larger matrices that you use MATLAB or some sort of calculator, either a determinant calculator online or potentially on a graphing calculator, because doing it by hand becomes very tedious very quickly. And I promise you do not want to do that unless you have to. So please try to use some sort of other tool to do that. So let's conclude with some practice problems. First, we have 2 like matrices here. They have the same dimensions. Try to add and subtract both of these matrices and see what you get, remembering that you're adding or subtracting corresponding elements together. The second is please multiply these 2 matrices. So they are dimensioned and set up in such a way where you can multiply them. You have a 3 by 2 matrix here and a 2 by 3 matrix here, so you should multiply them. And then lastly, as a challenge problem, find the determinant of the following 3 by 3 matrix. I encourage you to try those practice problems, and I hope you found this video useful for your class. Thank you.